I'm recording this session. So, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Today, yes, Jocelyn will have the lectures on ULearn. So, after today, I will post these lectures. The previous one are already on ULearn. So, today we will continue our discussion on Bode plots. Just once again, Bode plots are a systematic way of plotting the magnitude and phase of frequency response. It is convenient to see what frequencies will have what kind of magnitude and phase. And if we want to draw the Bode plot without the magnitude response without Bode plot, it would be like very inconvenient for two reasons. One of the reasons is like there are infinite frequencies. Number two is because of infinite frequencies, we cannot plot them on the same graph. So we use Bode plot, which is semi-log, as you can see in this particular uh, plot. We can see that it's starting from 0.1, 1, 10, 100, and it can go to like big values as well. So basically, this is a semi-log. So this one is logarithmic, and this is linear. On the y-axis is the magnitude of h times the log of 20 log of the value, right? Similarly, on the phase plot, this is again in semi-log plot, and it is in degrees. The angles are in degrees, right? So we saw in the previous thing that a transfer function can have these different types of components: constant term, a pole or a zero at origin, a simple zero or a simple pole, or a complex or quadratic pole. Right? Until last time we covered all these four for magnitude and phase. We'll do it again, and we'll do a question for this one. So just a reminder that for the constant gain, the magnitude is like 20 log 10 of that particular number. So whatever number is, we just put it here, take the log and multiply by 20. It will be appearing for all frequencies. Right? And for the phase is 0 for the constant term. Remember, constant terms means that it's just the real part, which is real plus imaginary for a complex number. Just the real part only, which is the x component. If x component is 0, the angle is 0, the phase is 0. So it's this 0. Okay. If somehow this k is negative, this will still be positive, but this angle will be 180 plus minus 180 degrees. All right. For a pole or a zero at origin, so let's consider the zero first, j omega. So it is basically we'll be taking the 20 log omega. So it is again for all frequencies, and we know for sure that log of 1 is 0. So we have a starting point to plot it. If we take omega 1, the magnitude is 0. Okay, and we go 1 decade earlier and 1 decade after. So one decade earlier prior to 1 is 0.1, and 1 decade prior to 1 is 10. So if we take 0.1 for this one, we'll get log of 0.1 is minus 1 times 20, we get minus 20 dB. So we get this as a point, you can see. Then of course 1 will get a 0, and for 10 we'll get a plus 20 dB, right? So basically the magnitude is increasing for every 10 times the frequency. 0.1 to 1, the magnitude increased 20 times. 1 to 10, magnitude is increased 20 times. This is called 20 dB per decade. So for a zero at origin, the slope is 20 dB per decade. You can see that the slope of this line is 20 dB per decade, and if it's a pole, it will be negative 20 dB per decade, like this. So very same, it will be centered at origin and will be negative 20 dB per decade. So far so good. And for the phase, for the zero, at origin, it will be 90 degrees. Remember, for the constant, it was 0. So it was 0. For a pole, for a 0 at origin, it will be 90 degrees. Like this. And if it's a pole at origin, it will be minus 90 degrees for all frequencies. Okay, let's move. For a simple 0, which is at Z1, what we're going to do is to find the magnitude, which is like this. So we just taking the magnitude of this one, 1 plus j omega upon Z1, log of it, and 20. So this is magnitude of this. For omega 0, since this is 0, since log 1, we'll see that h will be 0 because 20 log of 1 is 0. And for other frequencies, until like for higher frequencies, it will be the actual whatever the value is, because 1 is very big, this will be very big compared to 1. So we just get this one, the actual one. So if we want to plot it, we can do is 20 dB per decade for large values of omega. It's like this. So from 0 until Z1, since if omega is Z1, for example, so this will be 1. So it will be log of 2, which is actually like 3 dB. The actual value is 3 dB here. You can see this is the value at Z1. But again, this is exact. We're not plotting the exact one. So until Z1, we are safe. We just keep it 0. We assume that it is very small. And after that Z1, we'll have a line, a plot 20 dB per decade. So from Z1 until 10 Z1 like this, and this will be, so the slope of the line is 20 dB per decade for a simple 0. So we do nothing for whatever it is before Z1. At Z1, whatever the frequency, whatever this is 0 is, we take this Z1 and we increase 20 dB for 1 decade. We'll make a line like this. By the way, if it was a simple 0 but square, it would have been 2 zeros. So 2 times 20 will be 40 dB. So it will increase like this, 40 dB per decade. I'll show an example today. And once again, this difference is 3 dB at the frequency. So maximum difference is about 3 dB maximum difference, but not more than that. And the phase, you see, this is the phase because there's 1. This is basically, this is basically y, and x is 1, so just omega upon Z1. So if you keep omega equal to 0, the angle is 0. If you keep omega equals Z1, Z1 will be 1, and if omega is very big, will be 90 degrees. So we can see that from 0 to 90, it is going from 0 to infinity, but we're not going that. We'll center it at Z1 like this. We'll center it at Z1 and we'll keep it 45 degrees. So at the frequency will be 45, and we'll go 1 decade before and 1 decade ahead from 0.1 of Z until Z. So if Z1 is suppose 6, it will be 0.6 till 60 from 0 to 90. We'll consider this as the slope. So the difference in magnitude and phase is that for magnitude we start at Z1, but for phase we start 1/10 or like 0.1 of Z1. And of course, if it's a pole, it will be the opposite way. And this is all the same, except it will be from 90 at 0.1 and will go until 0 at 10 times the frequency. It's only happening between these two. For phase, it's only happening between these two extreme points. Z1 and P1 are called the corner frequencies. So these are the frequencies at which we have some change somewhere. A summary. So for the constant term, 20 log K, phase is 0 phase. For a pole, for a 0 at origin, it will be 20 dB per decade. But if it's like a square or a cube, so it will be 20 times 2 or 3 dB per decade. If it's like, suppose j omega square, it will be 40 dB per decade. So instead of 1 and 10, at 10 will be 40 dB or 60 dB or 80 dB and so on. And again, the angle will be 90 times that particular power here. Similarly, for the pole, it is like negative 20 dB, and starting at 1 or for the simple 0, we start at Z, this value Z, and we'll go 20 dB per decade. If it's once again, it's not just 1 0, but 2 zeros at the same point, same frequency square. So it'll be 40 dB or 60 dB and so on. And similarly, the angle from 0 to 90 for one centered at Z. So Z will have 45. So plus 45 and minus 45. We'll show you an example. Similarly, for the pole, start at P, go 20 dB per decade downwards, and from 0 to 90 downwards, 0 to minus 90 downwards. Okay, let's take a look at this example. And I'm going to, since we did this yesterday about the setting of this one, we remember we need the standard form. So the standard form is we want 1 plus j omega by something. So this 10 should go, this should be like 1 plus j omega upon 10. 1 plus j omega by 2. Okay, so 2 and 10 coming out, 20, and this times 200 will be just 10. Okay, so this thing is basically 2 taken out common, 1 plus j omega by 2. 10 taken out common, 1 plus j omega by 10. And 2 and 10 together cancels this 200 with 10. What do we see? We see a k. We see j omega, which is a 0 at origin. We see a pole at 2. We see a pole at 10. So far, so good. Anyone not following? Okay. If we expand it into magnitude, this is a magnitude once again, k and 0 and pole. The k has the angle 90 degrees. J omega has the 0 has the angle minus. This is the 10 is 0. J omega has angle 90. This is coming from the pole at 2. This is coming from the pole at 10. Since they were in denominator, this is this negative sign, right? And when we apply the 20 log dB, log is linear, not linear, but it can go inside. So it will be log 10 plus log j omega minus log of this and minus log of this, like this, right? And the angle is simple as that. The phase is like this. Okay, so in summary, there are 2 corner frequencies. We'll have a change of frequencies at 2 and 10. For both magnitude and phase plots, each term is sketched first by dotted lines. Then they are added up graphically to obtain the overall plots by the solid curves. How we'll do it in the exam, we'll see what kind of in the exam, in the test, you may have to arrange for the semi-log papers, I believe. I think you should get a pack of semi-log papers for practice as well, so that you can practice and later on attach it with your test and quizzes and exams. All right, so let me do this with you. Okay, so 20 log 10. It will be 20 log of 10. 10 log of 10 is 1, so 20. So for this term, we'll get a 20 dB for all frequencies. So this is basically the line. supposed to be dotted. All right, so this 20 is always there. Okay. Then we have a 0 at origin. Where do we sort of center our 0 at origin? Can someone remind me? Where do we center our 0 at origin? Can someone type maybe? Where do we do that? But like, where should I start plotting it? Where should I center it? Can you guys hear me? Can you guys hear me clearly? 10. 10. Okay. Actually, remember, for this j omega is available at all frequencies. Okay, and we have to center it somewhere. So what if we just put log 1 here? Yes, yes, Jocelyn, it will be 1. We'll center it at 1 and we'll go 20 dB like both ways. And since it's a 0, it will be a positive 20 dB per decade. So it is supposed to be like this. Like this. So this is 10 and probably this is 0.1. Is that clear? I repeat, for a 0 or a pole at origin, we'll center it at 1 because at 1 the magnitude is 0. And basically we can go 10 dB, 20 dB upwards, 20 dB downwards across 1 decade. This is 1 decade and this is 1 decade downwards. Is that clear? Everyone? Everyone following? Can I have a raise of hands? Keep them raised up. Let me see if everyone is following. Okay, so far so good. Arif, Atika, Shamila, Nazirul, Shakira. Are you following? Like, is it like forcefully raising your hand, or is there a question? Please let me know. Shamila and Atika, are you around? Are you on your PCs? Shamila is leaving. Please don't leave. Okay, Yuvan, you just maybe joined. I don't know if I can ask you, are you following or not? Okay, Atika still not responding. I hope that she can. All right, so let me proceed. Okay, thank you very much. You can like unraise your hands, and if there is something, raise your hand again. So next we have a pole at 2. So we'll come to 2. I'm assuming that this is 2, which doesn't seem like 2, but I'm assuming that this is 2. And this is 20. And this is 0.2. I'm assuming that. All right. First of all, a pole is in the denominator. It's down, so it's going down. 0 is in the numerator. It's up, so it goes up. You can see that this line that I just have drawn right now, it's going upwards. So it's plus 20 dB per decade. For a pole, it will be minus 20 dB per decade. Again, centered at the frequency 2. And actually, we don't need for this particular case. For let me just take this off. I took the point here out because before this it was 0. If you remember, it starts at, so we just take care of this point and we go 20 dB downwards for the simple pole. So I'm plotting it from here until here. This is my pole at 2. Okay. Right. So from 2 until 20, it has gone down 20 dB per decade, gone down, or like negative 20 dB per decade. All right. Similarly, the next one is a simple pole at 10. So it will start at 10 here and it will go until 100. So I'm doing it the same thing. All right. So we have everything done. This is for the constant term. This one is for the simple 0 at origin. This one is basically the pole, simple pole at 2, and this one is a simple pole at 10. Okay, now what we have to do is just add them up. And the good thing is that we have the corner frequencies. So yesterday I was not correct by having so many of the corner frequencies. We just need a few corner frequency, which is already mentioned, which is 2 and 10. So one of the corner frequency is 2 and the other corner frequency is 10. All right, so far so good. So whenever we see this yellow line, this is like the corner frequency. You don't need to draw it, but this is just for our understanding. So if you start from, let me bring the red one again. If you start from here, like actually for the simple, for the pole at origin, for a pole at 0, it's going for all frequencies. But we start at 0. We start at 0 because we are taking from frequency 0 until infinity. So from 0, what do we have? What can someone tell me? What are the things available at 0 frequency? At this particular point, what do we have? What lines do we have that we have to add up? Constant and, thank you, Inchin. Constant and there's one more thing. The 0, the simple, no, not simple 0, the 0 at origin. Once again, let me bring my pointer. This thing, this line is the 0 at origin, and this is the pole, simple pole at 2. Okay, but Mohiman said minus 20 dB. Maybe he meant like this, something like that. Yes. So at point 1 for sure. At point 1, if this is point 1, so this is the line that we know already. So what we can do is to add these 2 points. This is 20 and this is minus 20. So where should we end up at point 1? At point 1, what is the total magnitude available? At this frequency, what is the total magnitude available? This is minus 20 and this is plus 20. So where should be? 0. Yes, very good. So let me, this is my starting point in a way. Okay, and when we move forward, when we move this way, we will be adding these 2, right? So looks like there is minus 20 and plus 20. This makes it 0. And then this remains same, but this is adding up until this line, right? But we know that it is of the slope 0.1 until 1. So we focus 0.1 and 1, and we have to increase the magnitude by 20 because this is increasing by 20 in 1 decade. I repeat, this was 0.1 and this is 1. So this is 0.1 and this is 1. At this point, we have 20 and minus 20. So this is 0. Now we are adding this 20 with this increasing one. So at the end of this change, this will be meeting at 20. Right? So let me draw it. Let me draw with a different color that this is the resultant one. So from this point, we'll go, not a good one. Can I use, I have my, let me see if it works. I don't know. It doesn't work. Somehow. So what is this line showing? This line is showing 20 dB per decade plus. So at this point it is 0 because this is plus 20 and this is minus 20. The sum is 0. At this point this is 0 and this is 20. So summing up at the end is, so this line is showing the resultant of these two lines. Okay, but listen carefully now. What is happening beyond 1? Anything added so far beyond 1? I'm not reaching 2 yet. Anything adding beyond 1? What is the next? Yes, okay, nothing added. So we'll keep on going with the same slope. I'm keeping on going with the same slope until 2. So the way you want to draw it is to keep these points as your reference, but until the next corner frequency it will keep on going like that. So let me just simplify it for you. So this line will keep on going until the next corner frequency, right? Okay, now we have something added in the system. What do we have? What's added at omega equal 2? You can chip in. What's added at omega equal to 2? This one. What is happening here? It's a simple pole. And yes, very good. This is minus 20 dB per decade. This is happening. All right. So this means that now the magnitude which was at this point will be changed. How? Okay. The way it is done is that we talk about the slopes. 20 dB per decade, minus 20 dB per decade, or some other value, or 0 dB or something. So the slope of the first segment is 20 dB per decade. And now we are adding a line of minus 20 dB per decade. So the slope which was increasing like this is now added up with something like this. What will happen? Plus 20 and minus 20. Plus 20 minus 20. Previously was a 0 slope and plus 20 slope. So the slope started to increase. Now we have a 20 slope and a minus 20 slope. When we'll add them, will be a straight line or flat line. I will take it as a flat line. Yes, 0 slope or flat line. You meant the straight line. Okay, they're all straight line, by the way. Flat line. Okay, very good. So it will be like this. Okay, until the next corner frequency, which is coming at 10. I repeat. Let me just, for the sake of all of you, I'm doing it all again. I didn't want to remove the dotted lines. Okay. Okay, this is one, this is something, this is something, and can I use something to make a straight line that doesn't make any touching? Oops. Nope. Nope. Nope, sorry. Okay, so for the first initial one will be from 0.1 and until the next corner frequency with a slope of 20 dB per decade will be like this. And now that we have, this was plus 20 dB, this is minus 20 dB. When we add them up, will be a flat line of this until. Okay, now what? Now what change do we have? What new thing that we have? At omega equal 10, let me ask. Wait, don't reply, guys. Let me ask. Okay, if Shakira is here because you responded the latest. Shakira, what do we have at omega equal 10? What is this? You can unmute your mic and tell me. Shakira. Shakira. I will keep on calling you. Shakira, 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 Shakira. Please. Okay. Arif. What do we have at omega equal to 10? You don't know. Okay. This is. Why do you not know? Yes. Yes. Thank you. Leong is minus 20 slope. Yes, you're right. And this is because of this simple pole. Let me just. Yeah. This is because of this simple pole. And this is minus 20 dB line. Minus 20 dB. Are you following now? When I ask you, were you following or not? You're making me cry. Okay, anyways, now once again at the beginning in this phase, there was this flat line and there was this plus 20 dB. So we can see that this 20 dB slope positive is like adding up. After this line, we have this plus 20 and minus 20. So plus 20 minus 20 dB will make us 0 dB slope until the next corner frequency, which is at 10. 10 is coming from a pole which is showing a negative 20 dB. So 0 dB minus 20 dB will give you a negative 20 dB slope. So we can go from here until the next decade like this. You have to see this value. So this value could be maybe whatever the value is, we have to match this value here. We'll go on like this. Okay. Arif, now you copy or not? You're fast now, huh? Okay. So basically, once again, it's important to understand that we're adding different lines. Just adding up is no rocket science. By the way, I was thinking that there will be a time very soon that people will think, like right now we say rocket science to something very complicated, very complex something, but there will be a time soon that it will be very simple and people will say it's not rocket science for something very simple. Come on, it's rocket science. Anyways, so we're just adding these dotted lines for the each corner frequency, and for the magnitude plot, if there is nothing else coming, it will keep on going down. It will keep on going down like this. So we don't have to go very far, just some line could be enough. Okay. Okay. I think I should do one more magnitude plot first and then come to phase plot for the next example. So I'm going to the next example for the magnitude plot itself, not the phase plot. Is it okay? Or do you want me to do the phase plot and then go for the next example? I do one more magnitude plot and then come to the phase, or I complete this example and then go to the next example? Okay, thank you. I wanted that. I wanted just one more vote. Thank you. So this is basically the actual plot that we were expecting to see after all this effort. So you can see few things. This is 2 and 2, 10, 100, all these things, So we can see all these things here. So from point 1 until 2 was plus 20 dB. From 2 until 10 was a flat line, and after 10 was a negative 20 dB slope, minus 20, 0, and 20. Right? Just for the sake of completeness and understanding, this value is, suppose you can find out by calculating as well, but let's say it's 25. So it's 20 plus 5 here, right? So this should also be 5. So 25 minus 25. You just subtract minus 20 from this point and go to that point for 1 decade. Okay. Without confusing you further, let me go to the next example. Okay. So this is our next example. Can someone first of all tell me what kind of elements are here right now? What elements are here? Do we have a simple zero? Do we have a 0 at origin for this one? Do we have a 0 in this particular example at origin? At origin. Do we have a 0 at origin? Yes or no? Are you sure? Yes. Anyone else? Do we have a 0 at origin? We have a pole at origin. Yes. We have a pole at origin. This is a pole. This is a pole. This is a simple pole and this is a simple 0. But is this in standard form? Do we have a constant? It's not in standard form. Yes. Do we have a constant? I'm sure most of you will say yes. Do we have a constant in this particular example? Yes, very good. We have to make it first into standard form and then we'll see if there's a constant or not. So this is not in standard form. Let's bring it in standard form. So it's 5, 2, 1 plus j omega by 2. I'm taking this two commas, so that this is 1 and j omega by 2. And 10 j omega 1 plus j omega by 10. Like this time also we have 2 and 10. So 10 and this 10 cancels. We just have 1 plus j omega by 2, j omega 1 plus j omega by 10. So we have simple 0, pole at origin, and simple pole. All right. We have a slide available next to it. Don't have a slide next to it, so I have to do it here. Okay. So we're doing just the magnitude plot. So let's do it all the things. So once again, we have a pole at origin, 0 at 2, and a pole at 10. So the corner frequencies are let's call them 2 for the omega c, 2 and 10. Two, 10. This one is 0, so plus 20 dB, and this one is a pole, so minus 20 dB, and so on. All right, I have to copy the plot from there. I mean let me just copy this one. Duplicate slide. Okay. So let me go to the next slide. I have oh, this is a phase plot. Sorry, should have been a magnitude plot. Okay. So I am plotting the magnitude here. So what do we have? J, let me just simply call it pole at origin. How do we plot a pole at origin? That we center it at 1. Can you see it? And we go 20 dB plus minus. So let's assume that this is 0.1 and this is 10. Like this. Is that okay? Okay. Then we have, I believe, a 0 at 2. 0 at 2. So if this is 0, we will be going plus 20 dB from here. So 2 until 20, which is here. Can you see the lines, guys? Can you see the lines? I don't see. Oh, okay, yes, but don't see 2, 20. And then a pole at 10. So at 10 until 100, we have a this. Okay, let me draw the corner frequency margins just for the sake of. Okay. So what do we have from the beginning? The first thing that we have is this line. So let me make it solid until, let me use another color, solid until the cutoff next corner frequency actually going right. So at 2 we will have 0. So right now this is minus 20 and this is plus 20. At 2 they will cancel out each other and this will make a flat line until the next corner frequency. So this is everyone following? So this line is the pole at origin. Then this is because of this slope. And at 2 we have this particular line of plus 20 dB. This was minus 20 dB. So at this point they both will cancel each other. That's why we have a flat line until the next corner frequency. And at 10, we know at 10 we have another pole with minus 20 dB. So from here we will see this magnitude here. If it is let's say 4, so just 4 only, whatever the value is 4. So from 10 we'll go to 100 at 0. This looks like minus 4 actually, looks like minus 4. So minus 4, then we'll go to minus 24. And so on. This point should be, so this is minus 20 dB. All right. Can I have a raise of hands if anyone, no, actually raise your hands if you think you need me to show it again. Raise your hand if you want me to show it again. I can do the whole example again. Please don't be shy. This is an online class. Nobody's looking at you. So you can raise your hand. I won't tell your name. Everybody will know anyways. Don't be shy. Oh, by the way, do you feel shy in a regular class or in the online class? Because in the online class, everybody sees your name, but in the physical class, sometimes the teacher actually, uh, uh, I'm very comfortable in guessing, okay, who is following and who is not. I do that, but somebody put a message. How do we get, no, this is just a value. No, this is just whatever the value is. I just took a number. Minus 4 is not the value here. It could be the value on the plot. So just bring it on the y-axis. Is yes, it is based on the graph. Yes. I don't know the number, but whatever the number it comes. So whatever the value is, just plus 20 or minus 20 from that value for the next decade. Good question actually. He was asking, why do we get minus 4? It's not minus 4. It could be any number. Just go to the plot and see on the x-axis or on the y-axis what value is. Then you go plus 20 and minus 20 for the next decade. This is why I get minus 24 here for the whole decade period. And so for the magnitude plot, we'll keep on going, but for the phase, we'll stop at that particular frequency. All right, anyone, any question? Okay. One more example or I go to phase? One more example for magnitude so that we finish off magnitude and then we come to, yes. One more, okay. One more of the magnitude plot. So this is basic. This is what we just plotted. You can feel proud that you have done a complicated thing. This is our phase plot. Okay, let's take a look at this one. Do I have the? Let me copy this. Okay, I hope it will be enough. So can I say that we can convert this into standard form? So it will be like 1 plus j omega by 10 and j omega. And what should I take common from here? This is j omega plus 5. So 1 plus j omega by 5 square. There's a 10 here and there will be a 25 down there. Is that okay? Okay, so this is basically equal to 0.4 if I simplify it. One, not enough space. Okay, equal 10, 1 plus j omega by 10 j omega. Just to show you, it's actually 5, 1 plus j omega by 5 and 5, 1 plus j omega by 5. It's like 1 plus j omega. There was j omega plus 5 whole square, so I just put j omega plus 5 and j omega plus 5, and both of them will give me 1.5, so that's where I got 25. So it's 10 upon 25 is 0.4. 1 plus j omega by 10 divided by j omega, and 1 plus j omega 5 at actually square. So we have a constant term, we have a simple zero, we have a pole at origin, and we have a repeated pole at 5. So when we have more than, if we go back on the this one. So if it's like a repeated 0 at origin, it's like 20 times n. If it's like 2 or 3 or 4, similarly, if it's a simple 0 to the power n, it will be 20 times n dB per decade. Here we have 1 plus j omega upon 5 square, so 2. So we'll get 20 times n, so minus 40 dB per decade. Okay, we'll get a 40 dB per day, minus 40 dB per decade for that particular. Yeah. Okay, so let me go to the example now again. Yeah. So remember that when dealing with this corner frequency, some messages. What is this? When we're dealing with this particular corner frequency 5, we'll have 2 poles there, and that will get there. Okay, so let's start with 0.4. Log of 0.4 times 20 is, let me just use my calculator. It's 0.4 log is 0.39 negative times 20. It's approximately minus 8. So for this 0.4, 20 log of 0.4 is approximately -8. So if this is 0, so I make a line at -8. All right, are you following? Can you see the line? I don't see the line complete. Oh, now it's here. Okay, then we have a pole at origin. Once again, we'll center it at 1 and plus minus 1 decade ahead, 1 decade before, with a slope of -20 dB. So actually it's like coming, if it's, oh, I draw the spot not on the particular, yeah, it should be at 0. Yes, so something like this. Then we have a corner frequency of 5. If this is, I'm just assuming that this is 2 and 3 and 4 and 5. So let me assume that this is 5. Maybe this is 5. Okay. If this is 5, so at this 5, we'll have a slope of what? What should be the slope at 5? Can someone remind me? I just mentioned. What will be the slope of this pole at 5? Somebody mentioned -40. Yes, thank you very much. It will be -40 because it's a square. It's a square. So from 5 until, assuming that 1, 2, 3, 4, assuming that this is 50. So we'll go -40 dB. So from 0, this is 20. This is 20 minus 20, and this is assuming -40. So it will go from 5 to 50, which is something like this. So this was basically -20, and this is -40 dB per decade. All right, and then simple 0 at 10. So at 10, a simple 0, this will go from, now this is standard for us, 20 dB per decade. Okay, how many corner frequencies here? Yeah. We don't count origin as the one that we have to make any change. Okay, so corner frequency is 5 and 10. So let me draw my standard yellow lines at 5 and at 10. Okay. Okay, so in the beginning, okay, in the beginning we have -8 and -20 dB per decade. What will we see? Yes. Anything done? Okay. So we have a -8 and -20 dB per decade. What will be the resultant? But it's not -20, it's like coming from 20 something. So 20 minus 8 will be 12. So initially we'll start at 12, somewhere around maybe here. Twelve comes from where? It's 20 minus 8. Is that right? Yep. So starting from 12, we'll come down with a slope of 20 dB per decade because it's a pole. So somewhere like this, it will be, this slope should be our reference. So let's see. And if we go until 5. All right. What is the slope of this line? Minus 20 dB per decade. I'm looking at this plot that I don't have enough space to. Okay, anyways, what will happen now? The slope of the current line is minus 20 dB per decade. What is the next line that we have? Minus 40 dB per decade. So resulting will be minus 60 dB per. So we have to go down minus 60, which I don't have enough space here. But this should be like going down like this, something like this, until 10. So minus 60 dB per decade. Are you following? Are you following, guys? This particular thing now, this line is minus 60 dB per decade. So from 5 to 50, we'll try to make a line, but of course we'll be blocked at 10. But anyways, from 5 till 50, we'll be drawing a line of minus 60 dB per decade. Well, we'll stop at 10 because at 10 there is a 0. So at 10, minus 60 will become minus 40. I don't have enough space here, but it. Okay. Duplicate slide. I'm duplicating that thing. So at 5, it was coming something like minus 20 dB per decade, something like this. But then we'll go at minus 60 dB. 5 is maybe here. 5. Then 5 until 50. We're supposed to go 60 dB per decade down. So this is 20, 40, and 60. So it's supposed to go like this from 5 to 50. Are you following? But of course, it will be like blocked at 10 because at 10 we have a 0. So after 10, it will become minus 40 dB per decade. So this is minus 20. This is minus 60, and this is minus 40. Are you following? So this is what it looks like. Don't worry about, should I duplicate it? So you can see that initially it was going with a slope of minus 20 dB per decade, like this, until 5. At 5, we got a double pole, so it became minus 60 because minus 20 and minus 40, minus 60, until 10. Then we got a simple 0 that made it minus 40 dB per decade. All right. Is it okay? Is it okay to understand the concept? I give you a break here, maybe 5 minutes. Then we do the phase. Right? I break for 5 minutes.